our project is an AES 128 hardware implementation. Our group member includes Kadon, Austin, Z, and Wilson. So our goal for this project is to implement the advanced encryption standard 128 in hardware. It support for 128-bit key and data block size. Makes parse interface for system integration. And we're gonna make our design space efficient, and we're gonna optimize our performance. And the advanced encryption standard is a symmetric block cipher, and it replaced the DES as federal standard in 2001. The key characteristics for our AES, it has a 128 base fixed block size, um, and the key size, 10 number of rounds, and 4x4 battery supplies of state array.
So for the system architecture, we have modular design, we have a bus interface, we have a key expansion unit, we have a round processing unit, we have a controller, and then we have an Xbox, which is implemented kind of as one of the parts of the AES round, which will be talked about more later. But the bus interface has a 32-bit data transfer management, so it has its own control inside of it that manages that input or output on the data line. But it basically takes in the ciphertext, takes in the key, it sends the ciphertext, or it sends in the plain text initially to the controller, and then it sends the key to the round generator, which the round generator will end up making specific parts, its specific round keys for specific sections of the AES round that will end up returning the ciphertext back to the controller, and then the ciphertext will be sent back out on the data bus line through the bus interface. And so our design features include the AES, which is fully 128-bit compliance according to the FIPS 197. And then we have 10 rounds of encryption. So with inside the AES round, we do 4 steps times 10 different rounds. And that's according to that standard, just 10 rounds of encryption, which makes it almost impossible to crack. And then we use the SBox using the Boyar-Peralta method, which is part of the one of the steps of the AES round as well. It's just a lookup table essentially. And then we have that 32 bus interface for the data and key loading and unloading, and then automatic key scheduling. So that all happens through the controller. And so inside the AES round, we have 4 different steps. We have substitute bytes, we have shift rows, we have mixed columns, and then we have an add round key. So essentially the substitute bytes is a lookup table, which will be explained a little bit more in a second. But it's a lookup table, so it substitute each byte of that message with another one from a lookup table. We shift the rows, so there's a couple different rows. So they're essentially blocks of bytes called words that get shifted depending on the row. And then the columns all get mixed, so they all get shifted as well. So essentially we're just mixing up all of this information. And then based on the key, the round key generator takes part of that key and then it gets XORed into the actual message. And that happens, all 4 of these steps happen once per round. And as stated before in the last slide, we do 10 rounds. And then the bus interface, since it's 32-bit, you'd have to have 4 cycles waiting for a 128-bit key and or message with some other output lines.
So for the Xbox implementation or the substitution box implementation, one of our goals was to have space efficiency so that we can use less resources. So that's why instead of using a lookup table, we use the Boyer-Peralta optimization method, which in summarizing is just a 3-stage implementation that gives us a top linear transformation, a middle nonlinear section, and a button linear transformation. And that, like I mentioned before, allow us to reduce the area compared with all the area that we will have to use if we use a just plain lookup table, while we maintain like the efficiency and the security properties of the Xbox and the AES. We have a overall basic state machine operation. We are waiting for uh, the start of the if for the AES to be enabled. Once we get that signal, we go out from this idle state uh, and move either to load the block or the information that we want to encrypt, or load the key, which is the key is something that needs to be provided, the 128 bits key. Once we have either of those, we start the encryption, and that's the next step on the process. And during the processing, we do the round execution, where we make use of the Xbox, the substitutions and things that Austin mentioned before. And once the process is done, we have the actual output data, which is encrypted, that we can communicate or transmit. An important model on our AES is the key expansion process. The whole purpose of this process or module is to generate 10 different rounds of keys that we are going to use in the process of encrypting the information. So the basic of the key expansion process is we get a 128-bit master key, and with that master key we run 11 rounds. The first round is going to be use the same key, the original key, but then the next 10 rounds are going to generate different keys that we are going to use in the process. And this is just a summarize of how the algorithm works. It's just to display what we do during the process of generating the keys.
Some of the key challenges that we had were implementing the optimized Xbox in order to get the correct area reduction, as well as the timing and coordination between a bunch of the different modules like the bus interface, the key generator, and the AES controller, as well as we had a lot of synthesis errors from the way some of the modules were designed, which had to be redesigned a little bit and then implemented in a way that could be synthesized. Then the characteristics of our final system, it was synthesized at a frequency of 10 megahertz. It has a total of 28,000-ish instances, and it had a total slack of about 17.6 microseconds, with a total cell area of just over 1,300,000 micrometers squared. And that little image is the image of our final design implemented in silicon. Now, if we compare our design with what currently exists, the most common thing you find nowadays is many instruction set architectures. A subset of them that can be implemented is our instructions to process AES rounds. So you can do this encryption in multiple processor cycles. Another way you could also do this is just doing it in software, which is very common. There's plenty of libraries like the Python cryptography library. And then another way that's common to do this currently is just implement this on an FPGA instead of in hardware, just due to time and cost constraints. And then some of the future improvements we would do, simply due to lack of time in this course, is add support for decryption to see if we could pipeline the design to get faster throughput. We would add an interface to be able to use DMA or direct memory access with embedded systems, as well as add support for SPI or I2C integration to use those standard communication protocols, as our current design uses a proprietary communication protocol in order to get a faster throughput of 32 bits per clock cycle rather than a lot fewer that come with those other protocols. And then we would also try to optimize for power, because one of the main reasons for this design is to be used with more embedded systems that many run off of batteries or lower power sources, so it's better just to have a more power optimized design. And then the last improvement we would do is to just expand our support for the AES protocol, being other key sizes such as 192 and 256. And this concludes our presentation. Thank you. If you have any questions, please ask them.
Thank you very much.